Welcome to lesson 9.3 and 9.4. Your textbook splits this into two sections, products and quotients, but they're both pretty short, so I'm combining them to one. First, we're going to look at multiplying two functions or product of two functions. There's multiple notations for this, so we can write multiplication like you know, with just the two variables right next to each other. So fg of x, that's the same as saying f times g of x, which is the same of f at x times g at x, or if you prefer f at x, and then you can use the dot for multiplication, times g at x. Similarly with quotients, a couple of different notations. So we can write quotients or division like a fraction. So f divided by g of x is the same as f at x divided by g at x. Or we can write f divided by g with the division symbol of x. And that's, of course, the same as f at x divided by g at x. And these all four are equal to each other. So I could use the first one and the last one if I wanted. Okay, so we can multiply or divide functions, again, if the x values exist in both of the original functions and it doesn't result in me dividing by 0. So I have to think about that when I'm doing a quotient. The x values, again, remain the same, and I just multiply and divide the y values. So for some f at x and g at x, is it true that f times g at x will always equal g times f at x? And yeah, that one's going to be true. That's if you think about like 2 times 3 is always equal to 3 times 2. And it doesn't matter if I use negative numbers or fraction numbers, it's always going to be true. So yes, this one is always true. And then we want to think about, what about f divided by g of x? Is that equal to g divided by f of x? And then this is going to be very rarely true. So most of the time this is a no. It's kind of like our subtraction, right? Very rarely true. This one, remember, subtraction is true if f and g are exactly equal. This one's going to work if f at x is equal to either g at x or negative g at x, right? So if I put the negative g at x on the bottom or the negative g at x on the top, the negative will still just divide out. So that's going to work either way. Domain. So for x to be in the domain of the multiplication or the product, f times g of x, it must be in both the domain of f at x and of g at x. So this is similar to our addition and our subtraction. It's a little bit different for division though, because for division it has to be in both the domain of f at x and g at x, but also whatever I'm dividing by can't equal 0. So here I was doing f divided by g, so g can't equal 0. If it was the other way around, if it was g divided by f, then f wouldn't be able to equal 0. All right, in our first example, or I guess our second example, we've got f at x is a cubic function and g at x is an exponential function. So we're remembering those parent graphs. And what we're going to do here is graph both of the original functions on the same grid. We're going to state those domains for those original functions, and then we're going to use those graphs to sketch the multiplication or the product function. Then we're going to state the domain of the product function, and then we're going to think about what's the domain of the division function. So again, there's different strategies here for coming up with the graphs. Table of values is your most cumbersome, but it can be your most accurate, especially with something where I'm not really sure what's going on. But again, if I feel really confident graphing my cubic, I can do that. And then graphing my exponential, and then just looking for points that are on top of each other vertically and multiplying those y values together will give me my new result. So I would actually use that strategy most of the time. When I'm working in a limited space on a limited grid, I do like to know ahead of time what kind of values are going to make sense so that I can make a proper scale. So for that reason, I'm going to make a table of values. But like I said, if I had like a big sheet of graph paper, I probably wouldn't do that because I'm lazy and I think it's faster to just sketch the graphs. So I'm going to do x, and then I'm going to do f at x. So that's my cubic function. And then I'm going to do g at x, my exponential function, and then finally I'm just leaving space here at the end to do the product. So for this function, for the cubic function, you might recognize that I can factor this guy, and I get x times x squared minus 1, but that's the same as x times x minus 1 and x plus 1. So if you remember from your polynomial functions unit, this tells me the three x-intercepts of the function are 0, 1, and negative 1. that means that I kind of want to know what's going on between 0 and 1 and between 0 and -1. And for that reason, I'm actually going to use half values when I go down my x column. So I'm going to go with -2, -1.5, -0.5, 0, and then I'll do the same thing. Oh, I forgot one. Sorry, -1.5, -1, -0.5, 0, and then I'll go down the same on the positive side. It becomes a lot of values, but that way I don't have to worry about the big numbers that are going to pop right off my grid with enormous y values. So first, looking at the cubic function, I'm going to plug all of these x values into the cubic function, and I come up with these numbers. And I'm rounding to 2 decimal places throughout my chart. That's going to help me graph. Normally, I would prefer to not use decimals, but whenever I'm graphing, I need them to show the heights. And it's cubic. I'm going to see this. This cubic hasn't really been shifted around, so I'm going to see that odd symmetry here where the negative of all the and the negatives and the positives of all the values that I got on the other side. All right, for g at x, this is my exponential function. So we're plugging in all these x numbers as exponents now. So 2 to the power of 0 is 1. We remember that. 2 to the power of 1 is 2. 2 to the power of 2 is 4. And then for the halves, that's like for 1/2, I'm doing the square root of 2, which is about 1.41. And then here, thinking about like 2 to the 3/2, that'd be 2 cubed and then square rooted, or 8 square rooted, and that's about 2.83. And then I could do the same thing on the negative side. So remember, the negative exponent is going to do a 1 over thing. So I'm not going to see matching numbers here because this negative is now making it 1 over. And so I'm just punching these numbers in as exponents on 2 using my calculator. And again, I'm rounding these numbers to 2 decimal places. These are not all exact. All right, this is going to help me graph my 2 original functions. Before I do that, I might just want to take a look, because I see ahead of time here that I am going to sketch f times g. So I'm going to take a look at, well, what kind of y values am I going to see if I multiply these together? So again, I'm not worried about the algebra here of multiplying these. I've already got my 2 answers. When x is -2, I can come up with my new y value just by multiplying the old y values, and I get -1.5 for the first one. And then I'm just going to keep going down, and I'm just multiplying the 2 old y values together to come up with my new y value. Okay, so when I look at these values, what I notice is this last one is like enormous, and all my other y values are somewhere between -6 and 5. So I'm not going to graph that last value. I'm going to just cross it off my list. I'm not going to worry about it. And since I'm doing that with the 2, I'm probably not going to worry too much about the -2. I could graph g and f times g for -2, but I'm probably not going to worry about f. So for my y scale, that tells me I want to be able to see down. If I'm not going to worry about this one, the smallest one I see is like -1.88. So I want to see down to -2. And the biggest one I see then is 5.3. So I want to see to 6. So somewhere between -2 and 6 for my y-axis. And then for my x-axis, I want to see from -2 to 1.5. So like -2 to 2, pretty much. All right, so I'm throwing my axes on there. For my x values, I want to see those halves really clearly because I know that I graphed each one of those, and I want to be able to see from -2 to 2. And then for my y values, making sure I can see all the way up to 5. And then down below, labeling those as well. All right, so I've got my scale now. I just need to plot my my points. So I'm going to use colors here to help me out. I'm going to do f of x in black, and then I'll label it as well. So again, for my f of x, I can't see the -2 value, but at -1.5, I'm at -1.88 and 0. Then at a half, I'm at 0.38, 0. All right, and this does look like a cubic graph. And here I know, like I can see I crossed it off my table, but I know that 2, it goes through 6 here. All right, so there's my f at x. Now we'll do g at x. G at x is my exponential. So I know my exponential has a y-intercept of 1 if there's no transformations. And so those are my basic ones, and you can add all those half ones in if you want as well. Remember that exponential has a horizontal asymptote just on the left-hand side of this graph if there's no transformations. Oops. I did it again. All right, that shouldn't wave in and out. Anyways, for my next graph, for my f times g, oops. So this is g at x. All right, we're going to go over to -2 and down to -1.5. And I'm just plotting the points. So I'm looking at my x values in the first column and my y values in the last column. So notice that hump got even lower in here. But this guy is connecting like a curve in here. This one got lower. All right, and so here this guy stretched out a little bit lower, and then he's coming up. Oof. Again, I hope that you're doing a better job than me on my tablet here. That's not even a function anymore. That doesn't pass the vertical line test. Okay, there we go. And this is FG. And actually, if you did continue and take a look at this graph a bit more, I do know that this is a point here, but then it actually starts to curve back up. This is an interesting graph, and then it actually comes up, and there's a horizontal asymptote. That's 0. That's just for interest's sake. You wouldn't be able to show me that unless you use Desmos. And you can take a look. It's an interesting thing that it does pull up back up to 0 because this guy is getting closer and closer to 0, but it's being multiplied by this guy, which is spiking down to like -infinity. So it means that this guy's getting closer to 0 faster than this guy's getting to infinity, right? These numbers are much, much smaller than these numbers are big because they're pulling back up to 0. So it's just an interesting little tidbit. Okay, so part B asks us to state the domain of the two original functions. So hopefully we remember that the domain of f, a cubic function, is just the set of real numbers. And then the domain of g, that's our exponential, again, just the set of real numbers. So when I look then in part D at the domain of f times g, it makes sense that that domain is also going to be the set of real numbers, because for product functions, I'm just combining the original domains. So part E, we want to think about g divided by f. And the order is important here. I am doing g divided by f of x. So I want to think about, first of all, where will this guy equal 0, because I don't want to divide by 0. So that's what I'm thinking about. Now, remember above that we actually already factored out f at x, so I'm going to rewrite that factored version. It was minus 1 here. So f at x is equal to x times x minus 1 times x plus 1. And you can also just use your graph here. I can see that the x-intercepts on the black graph is my f graph. So the black graph shows me that there are 3 x-intercepts. And that means that if I was looking at the domain of these, I obviously can't use these x values or I would end up with an undefined answer. Oops. So x cannot be any of those x-intercepts of f. Otherwise, what I was thinking about was the domains of the original 2 functions, and there were no restrictions there for me to also include here. So I'm all done that question. Oh, and that's the end of today's lesson. Enjoy your homework.